Hi, now that we discuss the negative binomial models. So this is basically very similar to Poisson model. So similarly to the Poisson regression model, the negative binomial model fit the regression model. The probability of y is equal to yi that follows the negative binomial distribution with parameter mu and k in the previous slides. And the log of mu I is equal to xi transpose beta. So this is for each observation. So each observation have expectation, and that is dominated by this mu. And here the k is additional parameter. So at first the nb mu k is the binomial distribution, and the mu and k are the parameters. And so this means that the mu part is very similar to Poisson distribution, but still that we have additional parameter k. So we can flexibly adjust the variance of y. So often it leads to a more accurate model. And also this model specifies an exact distribution of y, unlike dispersed Poisson models. So dispersed Poisson model also can adjust the variance parameter, but we don't really know the distribution of y itself. Just we artificially introduced the variance parameter, but here we have meaning. So the mu and the k are parameters, and the k has the meaning that this is the number of the success when we evaluate the number of failures before that. Hi, that we now have an example for negative binomial models. So this example is the solder skips in the printing circuit boards in AT&T. So the number of skips. So this is the response variable. I would say maybe y. And we have several predictors: the opening, the solder mask, and the pad type panel. So you can see the exact definition of these variables in the help of the solder dataset in the faraway library. So we have basically 1, 2, 3, 4 categorical variables and the numeric variable to explain these skips. And skips, since we have many zeros, that we want to see what's the distribution of this. And this is the histogram of skips. So most of the time that is 0, that is about the 300 observations, then 1, 2, 3, 4, 5. So it may be fitted by the Poisson distribution, but we will see whether that is enough. So this is at first the fitting Poisson regression. So Poisson regression is more basic than the negative binomial regression. So that we fit this. So the GLM function and the family Poisson. Then we see that these parameters, and actually that we have many levels for several variables. You can see the opening have 3 levels. So the 2 additional levels in addition to the intercept, and some other variables have the multi-steps. So I just omit several rows, but basically we get all the coefficients and all the z values and the test results. But overall, the model doesn't have a good fit because the residual deviance is the 1829 on 882 degrees of freedom. So basically, this follows chi-square distribution with this degrees of freedom, and the chi-square distribution have the expectation equal to the degrees of freedom. So that means the 882 is expectation, and it's almost normal distribution. So this is the sum of 882, the independent squared normal random variables. So 1,800 is too large, I would say. So if we test this one, so that means that we have the ones 1829 here, and the degrees of freedom 882. Then if we make distribution, the PDF, then we have 1829 at the very right tail. So 1829 is the very almost the far right of the distribution. So this probability is almost 0. So the model is insufficient against saturated model. So the model is rejected against the saturated model. So we have to improve this. Maybe that we missed some variables. And textbook have another example of the fitting the skips on the square terms of these variables also. Actually the interaction term. So that we have many combinations, but it sounds that still it's not sufficient to explain this response variable. So now that we start, we try the negative binomial, the regression. So negative binomial regression is done by glm.nb function. So that function is the library MASS. So at first, the load the library, the install and load library. Then we can fit this. And again, we have got all the coefficients and the parameters. And basically, we have the same model, but we have a little more flexibility because we have expectation and variance explained by the 2 parameters. And actually, the 1 parameter is here. So this is the parameter k. Basically, the number of the successes that we choose. And then we have so another parameter, mu. So mu is explained by these observations. So we fit this, but we have additional parameter k here. So so this variable makes mu. So actually the log of mu is equal to the x beta, and this x variable are here, and the beta is this coefficient. And so that we have mu, but also we have k. So we have 2 parameters. So we only added 1 parameter, but the result gets much better. Residual deviance is 1008. In the previous slide, the 1829, so it gets 800 smaller on 882 degrees of freedom. So still, the 1008 is larger than 882, and it turns out that still it's rejected. The model is rejected against the saturated model. But the situation gets much better, and the p-value still the significant, but it's much better than the previous model. So, so this is the one example of the fitting the negative binomial model. And another way to fit the negative binomial model is just use the GLM function with the different family, the negative dot binomial. And you can put the k value here, but this function does not optimize k. So you have to put k manually. So if you put the many different k's, then you can compare the result, but basically the k should be given. Yeah, and the one problem of this using GLM function for negative binomial distribution is that the k is fixed. So it estimates mu, but also the R introduces the dispersion parameter for the negative binomial distribution. So this is somewhat contradictive because we use negative binomial distribution because we have 2 parameters. But actually, we have to fix one. Okay, so still we can change this one and we can optimize it manually. But we have 2 parameters to explain the variance. But the R introduces another dispersion parameter. So it's not really what we want to do. So if we introduce in dispersion parameter, anyway, the model is not really the concrete. So we don't really know what distribution we assume. So in such a case, there is no meaning to use negative binomial. Just we can use Poisson distribution with additional the dispersion parameter. So I think that it's better to use the glm.nb function in the previous page. So these are the examples of the negative binomial models.